Hi guys, thank you for rejoining us after some little technical difficulties. Today's LiveLab is going to be about gravity, and in more general terms, it's going to be about general relativity. It's kind of a little science joke for you there. But before we get started, we just wanted to say that we're really happy to be doing all this stuff with you guys, and these LiveLabs work best if it's more of an interaction between us. So if you guys have any questions that you want to ask about the topics we're going to be talking today about, general relativity, gravity, Einstein, and like a little bit of my boy Isaac Newton. If you have any questions about those, feel free to ask them. Katie is behind the camera. She's taking all of your questions. She's in the chat. And she can always ask me, and then we can get that dialogue going. Alex is also here. He's working our tech. He's doing some really fun things like clicking buttons every once in a while and making sure that my mic works most of the time. Anyways, without any further ado, gravity. Gravity has been one of the weirdest things in our history. It's one of the 4 fundamental forces, and it's one of the ones that we didn't know a lot about for the longest time. Now, back in the day, there was this dude who had to go into quarantine because of the plague. And during his time in quarantine, he developed the law of universal gravitation. That dude's name was Isaac Newton. And for hundreds of years after his development, we used his laws, and they worked 99% of the time. But there was a few edge cases, maybe 1% of the time, where they didn't work. And one of the most common sources of frustration for astronomers in particular was the orbit of Mercury. Using Newtonian physics, they could tell where Mercury should be, but it wasn't there. It was somewhere else completely. And no matter how much they looked at their work, they couldn't tell that they'd done anything wrong. In fact, the predictions themselves were wrong. And it wasn't until the early 1900s when a dude named Albert Einstein came up with his theory of general relativity that we were able to solve these questions and then a whole bunch of other questions that we didn't even know that we had yet. Now, obviously, the topic of general relativity is crazy. It's hard. It's a college-level course, if not even higher. I have a note card, and I've restricted myself to 1 page of it, and you'll see me occasionally looking down to refresh my memory about certain things. So Einstein's solution revolved around this first fact. When you are on the planet Earth, you are feeling a force downwards, and that's gravity. We know this, right? But what we don't realize is if you were in a small room where you couldn't see the outside, you actually could not tell if you were standing in a gravity field or if you were standing in an elevator that was accelerating upwards at the same acceleration of the force of gravity pulling you down. Or if you were more likely in a rocket ship that was accelerating upwards, you would feel the same gravity pulling you down. Without any external reference frame, we couldn't tell the difference between being in an accelerating reference frame or in a gravitational reference frame. So Einstein looked at this and he said, okay, so gravity and these imaginary forces that we feel have to rely on something else. They have to have some specificity to itself. You can go with that word however you want. And so what he did is he did a bunch of math. He did a bunch of predictions, and we don't have to go through all of those things because the most important part of it is that mass and energy together work to warp space and time itself. I'll let that sink in for a moment. Because that's weird, that's insane, that the Earth is warping space and time itself. We don't see this happening because it's happening in a dimension higher than we humans can perceive. But we have a really cool representation of this setup right here. Here at AstroCamp, you may have seen this before. We have something known as the Vortex Table. Woo! Dramatic music cue. Yeah, fantastic. Now, this Vortex Table is a helpful model for us to show us what the theory of general relativity acts like. It's not a perfect model. There are some places where it breaks down, but for the most part, it helps us a lot. Now, as we can see right now, it is completely flat. There's nothing on it. This is an example of space-time without any mass or energy inside of it. And in this case, space-time itself is flat. If we were to draw lines on this table, then they would be completely straight lines in whatever direction we view them in. But when we take something with mass and we put it onto the table, such as, I don't know, the planet Earth, we can see that space-time around the planet Earth curves. Okay, so what, you ask? Let's say we have another object, something very, very small, such as a rocket ship or a person or an asteroid. And if we put it on the outside of the gravitational well of the Earth and let go of it, we can see it accelerating directly towards the Earth. This is the force of gravity at work until it hits the Earth, and then there's something else to prevent it from collapsing any further, aka the crust of the Earth or the chair that your butt is currently sitting on, so on and so forth. With many different objects, we can see that, well, they try to stay in an orbit, but this is a breakdown of our model. In real life, space doesn't have friction, or if it does have friction, it's negligible enough that we don't have to worry about those kinds of forces. But in our table, however, we do have friction, so if I try to launch an asteroid into orbit around the Earth, we can see it going around and then slowly falling into the Earth. Now, Einstein's theory of general relativity helps us predict that we can, in fact, have things in orbit. And Newton himself came up with these ideas a long time ago. And for the most part, they stay the same in both Newtonian and Einsteinian physics. But there are few times where it does break down. And I mentioned this before. The orbit of Mercury is very, very strange. Astronomers, when they observe where Mercury is and try to make predictions about where it should be, could not come up with an answer until Einstein came here. And there's no really good way for me to show it, but I'm going to show it to you on this table anyways. So let's pretend like the Earth is not the Earth and is in fact, well, I'm just going to change it out so it's less confusing. So this is the sun. It doesn't really look like the sun, but we're going to pretend like it is. And going around the sun is a very not-to-scale representation of the planet Mercury. Newtonian physics have... Oh, do we have a question before we move on?
Yeah, so Maddie would like to know, do they orbit because of something bigger, Earth, bends time or mass?
Ooh.
Yeah.
Anything with mass will bend space and time. So let's say we have two different objects inside our space-time. We can see that both of them are exerting a gravitational force. Obviously, the more massive one has the bigger gravitational force. It bends space-time more than the smaller object does. But they still do have their own gravitational pulls. Very good question. But back to where we're talking about Mercury. So if we have Mercury going around the sun, the orbits of the planets are not perfect circles. They're actually more like ellipses, like this, ovals. This is an over-dramatization of actually how far away it would be, but it is still a decent representation. Now, with Newtonian physics, we would expect it to stay as the same ellipse all the time. But general relativity tells us that those ellipses can actually change. And as we have Mercury going around like this, it actually starts to change its ellipse going around the sun. And so it's never in a predictable place unless you know the correct math. Just one of the many reasons why Sir Isaac Newton is kind of a chump. Okay, so quick review. Space-time bends when there's something with mass inside of it. Thanks to one of Newton's earlier observations, though, his theory of special relativity, we know that energy and mass are interchangeable. You guys have heard of the equation E equals mc squared. This was one of the most popular things that Einstein ever did, one of the most important things about the universe that he discovered, that energy and mass are just two sides of the same coin. And so whenever you have something energetic moving through space and time, we also see the bending of it. Now, I don't have a really good way of representing energy in this situation, but the way that we can think about it is if you were going to go really, really, really fast, your mass would start to not actually increase, but appear to increase the closer you got to the speed of light, until you were about as close to the speed of light as you could, and you couldn't attain any more energy just because the laws of physics say that you can't do so. But these things are really interesting to us because we can actually see how the gravity wells manipulate other kinds of energy, such as light. So as we all know, light is a photon. It's a particle, but it's also a wave. And as it travels through space, it does so in a straight line. So if I take this marble right here and I roll it across the table, it's a straight line. It's pretty easy, right? But now let's put Earth back in here and let's roll the marble one more time. And I want you to watch carefully. I want you to think, is this a straight line or is it curved? Okay. It's pretty obvious that that was curved, right? Okay. Yes, it is pretty obvious that that was curved in our reference frame. However, if we were to, I don't know, attach a tiny little chariot to the back of this marble and ride behind it like we were following the photon, in our reference frame, this would actually appear to be a straight line that the photon takes in its path. Let me show you again real quick. And I want you to try and imagine if we were in space, not in this weird curved area, what this would look like. Yeah, I know, it's not super cool. But the way that this is cool is that Einstein made these predictions back in the early 1900s. I think he finished his theory of general relativity in 1917. Maybe it was 1921. Maybe it was earlier than that. Either way, the early 1900s, and about 100 years later, in the late 90s, I guess that's 80 years later or so, astronomers pointed the Hubble Space Telescope up at different parts of the night sky. And they started to see some very strange photos. These photos were of a star or a galaxy with this weird ring going around it. And they realized that due to the massive gravitational force of the object that we are looking at in the center was manipulating the light of the light that was coming from the object behind that object. I know I just said the word object 1,000 times. Essentially, we're seeing two objects that are one right behind the other, which normally we would not be able to see. But due to the fact that gravity can bend light, allows us to see directly behind this thing, which is an insane proposition. We have learned so much about our universe by being able to look behind other objects because they're so massive. Now, I can give you a representation of what that looks like on our table again. So if we have our table and we have two different light sources coming from different areas like this, you can see that the way that they go around a massive object sort of makes them appear weird. This is what gives it those halo-looking effects. In fact, we call these objects Einstein rings. We also use the term gravitational lensing. Some cool stuff. So, one of the other predictions that general relativity gives us is the presence of black holes. If you've ever heard of a black hole before, there are these mythical, scary things out in outer space that are doomed to suck the Earth in and destroy us all. Honestly, they're kind of boring. I mean, they're really, really cool, but there's some neat physics that are associated with it due to general relativity. So for instance, we have the Earth right here, and we can see it bending down. But if we have something that's even more massive than the Earth, then the table will bend even further. And if we put something even more massive, and then something even more massive down here, you can see that space-time continues to bend down and down and down even further. There comes a point when there is so much stuff in so small of an area that it actually causes a sort of tear in space-time, where no matter how far down I reach, I can never give anything inside the black hole enough energy to escape. We have these tears in the fabric of reality where it doesn't seem like anything can get out of, and that's actually very true. We've directly observed black holes for the first time in this past year. But we've known about them for a very, very long time because of indirect observations. We see a giant gravity well where not even light is escaping, and then we see a small star orbiting around this black, dark gravitational object until maybe eventually it disappears. Sweet. We have questions? Oh my goodness, I love questions.
So can planets collide? Like, would they ever crash into each other if they're orbiting the same thing?
If they are in a stable orbit with one another, no. What I mean by stable orbit is two things that have mass. Let's see if I can find a good way to show this. The collisions that we're seeing inside of our model here are due to friction. So if we have two objects to begin with, right, like one small, one big, they're each exerting their own gravitational force. And if they're orbiting around each other, they will eventually end up in the same place. But if we have two objects and then a third object joining, we can see that the second object has a localized gravitational field. That didn't work too well. Let's back up. We can see the other one has a localized gravitational field, kind of. But then obviously the Earth is much stronger. So planets do collide in real life, but not if they are in a stable orbit with one another, and not really because of general relativity. Did we have another question?
That was from our chat, but we have some others if you'd like.
Sure.
Yeah, can you tell us about like gravitational waves?
So gravitational waves are a prediction that Einstein made due to the theory of general relativity. In the same way as going to the beach and riding the waves, or standing in a pool while somebody jumps in and does a cannonball, space and time has a similar construct. And it wasn't until like 2 years or something ago that gravitational waves were first discovered. And they were discovered because two enormous black holes collided with one another and then send little ripples out into space. And the way that we detect these things is we take two objects and we measure them about, I don't know, a meter away from each other. For those Americans out there, in freedom units, that's 3 feet. So when they're 3 feet away and we detect with very, very sensitive equipment, as the I can't do this without gravity affecting my results. We can see the gravitational waves are slightly moving them back and forth from one another. And when that happens, the distance between them becomes slightly more and slightly less than 1 meter or 3 freedom units. In that case, we can tell that it's not those objects that are moving, it's space-time itself that is fluctuating, getting bigger and smaller. You guys may have heard of the fact that the universe is expanding and accelerating. This is due in part to general relativity. This space-time itself is the stuff that is expanding. It's making things get further away from one another. But it looks like we have another question.
What happens when you go into a black hole?
Ooh, very sad things. So the easy answer is you die, but the harder answer is how you die. Let's pretend like this is a tear in the table right here, and we can do a small demonstration of going into a black hole. Man, I wish we'd gotten some like clay or something to do spaghettification. Man, I'm just now realizing that. That's what we're gonna use a balloon for. Haha!
You said we didn't need them.
We need a balloon. Let's pretend like this balloon is me. I'm not going to even inflate this balloon, but we at AstroCamp will always use balloons for demonstrations. Here on Earth, the difference in the gravitational pull between our feet and our head is negligible, but it exists. In fact, if you've ever heard of the term tidal forces, it's what causes the moon to be attracted to the Earth and for only one side of the moon to face towards the Earth. And that's because the Earth has a stronger gravitational pull on the close side of the moon than it does on the far side of the moon. Tidal forces are what will kill you in a black hole, if the radiation and the vacuum of space and everything else didn't kill you first. So, if we pretend like this balloon is me, and that the place where I would inflate the balloon is my feet, and the very large spot is my head, if we go to our black hole and we lay our balloon flat down here, the amount of gravity on my feet is so much larger than on my head that I accelerate faster towards the balloon, towards the black hole with my feet than my head, and I get stretched out and stretched out and stretched out. And the greatest word known to science mankind is spaghettification. Your body will turn into a piece of spaghetti. This balloon example is actually pretty good. I really like it. Yeah. I'll rate it like a 7 out of 10. Very good. And then, one thing that I've been saying a bunch lately, and I haven't explained it at all, is that this right here is the fabric of space-time. We've been talking a lot about space, but we haven't talked much about time at all. When you are falling into a black hole, the deeper you are in a gravity well, the slower time will go. Now, to make this a little bit more abundantly clear, let's say we have a blue person who is very close to the black hole, and then we have this orange and yellow person who is very far away from the black hole. If they both started a watch at the exact same time and then stopped it at 1 minute, for this person, they would see this other person's watch stop at maybe 30 years. Whereas this person would see this person's watch stop at like 5 seconds. So time is relative, especially when you're close to a massive gravitational object. In fact, I'm about to say something that I really will regret. There's this movie called Interstellar that there's a lot of really good parts to that movie and a lot of really bad parts to the movie. One of the really good parts of that movie is when they go to a planet that's close to a black hole, and when they leave that planet and rejoin their friend has aged 40 years. Well, it's only been about 14 minutes for them. So in our case, if we were watching somebody else fall into the black hole, we would see them getting slower and slower and slower and slower until they appear to us to stop moving entirely as they approached the event horizon of the black hole. It's crazy stuff, you guys. We have a few more minutes if anybody else has any other questions. But
yeah, can you talk to us about a little bit about like what is dark matter?
So dark matter doesn't have a whole lot to do with general relativity, but it does have something to do with our universe as a whole. What we call dark matter, we call dark matter because of two reasons. Reason number one, we have no idea what it is. And number two, it doesn't react with electromagnetic forces, which means even though it creates these gravitational fields as predicted by Einstein's theory of general relativity, it does not associate itself with things like light or touching or electricity or magnetism or anything like that. And it actually makes up 85% of all of the mass in our entire universe, which is an insanely high number to me, to the fact that we don't even know what it is. That's what dark matter is.
Back to what we were talking about with time and stuff. Do astronauts age differently by being in space?
Yes, astronauts do age differently by being in space, but that actually has more to do with how fast they are traveling than how close or far away they are from a gravitational field. Much how we were talking about, it's impossible to tell the difference between if you are in a gravitational field or an accelerating rocket. Astronauts in space are traveling faster than humans are. So when an astronaut goes and serves 3 months up at the International Space Station and then comes down, that astronaut actually has spent 3 months, 0.0000000000001 months in space. That's not an accurate number. I just threw it out to show you guys the difference between. But yes, they do age a little bit more quickly up in space than we do down here on Earth. Okay, do we have another question?
Yeah, we probably have time for one more.
Okay, sounds good.
Can you tell us a little bit about the speed of light and why things get so wacky near it?
Yeah, the speed of light is the universal speed limit. And in fact, nothing in the universe can go faster than the speed of light. There was an experiment done a couple of years ago where they thought they had seen some neutrinos go faster than the speed of light, but it turns out that their data was messed up and that wasn't actually true. Fun fact, the speed of light was actually discovered by accident. I can't remember the dude's name now, but he was, I think he was Danish. I'm not going to even try to guess. He was an astronomer who was looking at the moons of Jupiter, and as he looked up at them, he was like, they should appear right now. Oh, now they are. Huh. That's very weird. And he used that discrepancy of when they should have appeared to when they actually did appear and calculated the delay, and then he realized, oh, then light must be traveling at a certain speed, and the amount of time it took to get that light here can tell me what the speed of light. I just discovered the speed of light, guys. And then it went from there. Einstein's theory of relativity, especially his special theory of relativity, which is a special case of general relativity that only applies when the space-time is flat right here. It tells us that the closer you get to the speed of light, the crazier things get. Things actually get physically shorter, and time gets physically longer when you are going close to the speed of light. Old Romer, that's his name. Yeah, it sounds like a Texan guy, like, oh, you hear about old Romer back there? Yeah. Now, that's about all the time that we have for you guys today. This was a heavy topic. I hope you guys learned something. I learned a lot about researching general relativity this last couple of weeks, but we just wanted to say thank you guys for coming out. We really appreciate the audience that we get from this. We appreciate your questions and your participation. Next week, we're going to be doing a lab on density. It's going to be a really cool one. Is it Katie or is it Alex who's doing this one? It might be Katie, but don't hold her to that. Just send her tons of messages that you want her to do that. But until then, we'll see you guys. Make sure you check out our other content, and we love you guys very much. Goodbye! Goodbye!